One of the biggest myths in fitness is that exercise tears your muscles apart. You've probably heard it before, you're ripping muscle fibers when you train. It sounds dramatic. It sounds hardcore. But in most real-world training, that's not actually what's happening. Severe muscle fiber damage, the kind where sarcomeres are completely disrupted, does exist, but it's mostly seen in lab studies where muscles are electrically stimulated, not voluntarily contracted. In normal training, even hard exercise, this level of damage is rare. Outside the lab, true fiber necrosis, cell death, is observed in only a small percentage of fibers, usually after extreme events such as marathon running. And those fibers go through a much longer, more complex repair process. In fact, studies comparing voluntary contractions to electrically stimulated ones show far less structural disruption when the muscle is voluntarily controlled, even after hundreds of maximal contractions. This tells us that most real-world training causes reversible disruption, not structural catastrophe. So no, your muscles are not being shredded every time you train. But if your muscles aren't tearing apart, then what's causing them to be damaged from exercise? What's really happening is micro-level disruption inside the muscle fiber, primarily when a muscle is producing force while being stretched, which is known as an eccentric contraction. This triggers inflammation and temporarily reduces force production, but it's not catastrophic damage. The key player here isn't tearing. It's calcium. During eccentric contractions, several things happen. First, stretch-activated calcium channels in the muscle membrane open, making the membrane more permeable. Additionally, the high stress that occurs can disrupt microstructures, such as the T-tubules, which run across the muscle fiber and are stretched when myofibrils slide past each other, following non-uniform sarcomere lengthening. This can result in a phenomenon known as sarcomere popping. Indeed, structural changes in these components have been reported. These disrupted T-tubules may allow calcium to enter the muscle fiber, and because they are closely linked to the sarcoplasmic reticulum, this disruption may also promote calcium leakage from internal stores. However, most of the calcium leakage seems to come from the stretch-activated ion channels. Secondly, the internal calcium release channels within the muscle fiber also begin to leak more calcium. At the same time, the pumps that normally move calcium back into storage, known as the circa pumps, become less effective over the next few days. The result? An abnormally high calcium signal inside the muscle fiber. That excess calcium activates enzymes called calpains. Calpains don't destroy the muscle, they disassemble it. They tag specific structural proteins for breakdown and recycling. This temporarily disrupts muscle contraction and strength. As this process is occurring, inflammation increases blood flow and activates immune cells that help clear debris and rebuild new proteins. But the inflammation here isn't bad. It's helpful. When you see images of damaged muscle fibers under a microscope, you're mostly looking at controlled protein disassembly and rebuilding, not ripped tissue. In other words, the muscle isn't being destroyed. It's being remodeled. That remodeling process can temporarily weaken the muscle. This muscle weakness after eccentric exercise is largely explained by calcium-driven protein breakdown. Key structural proteins that stabilize sarcomeres and transmit force become temporarily disassembled, reducing efficient force transfer and generation. This disruption can also lead to partial disassembly of contractile proteins and degradation of calcium-handling proteins, further impairing force production. In addition, neural factors such as pain and swelling reduce muscle activation. Together, these processes cause short-term weakness without destroying muscle fibers, which rarely die under normal exercise conditions. So when we talk about muscle damage, we need to rethink what that means. It's not about tearing fibers apart. It's about calcium dysregulation, protein turnover, inflammation, and remodeling. And interestingly, the amount of disruption seems more related to how much the muscle is stretched while active, not necessarily how heavy the load is. Other mechanisms may also contribute to muscle damage, such as increases in sodium, which can disrupt acid-base balance and osmotic equilibrium. Elevated levels of free radicals may also damage cellular components. However, there is little doubt that calcium plays an important role. Your muscles aren't fragile. They're dynamic systems constantly breaking down and rebuilding themselves. An understanding that changes how we think about soreness, recovery, and training itself.